Welcome you all. In this video, we are going to see the existence and uniqueness of solutions to first-order equations. So first we will see the definition and result used in that theorem. So the successive approximations phi k defined by phi naught of x equal to y naught, phi k plus 1 of x equal to y naught plus integral x naught to x, f of t comma phi k of t dt exist as continuous functions on the interval I such that modulus of x minus x naught less than or equal to alpha, which is the minimum of a comma p by m, and x comma phi k of x is in R for all x in I. Indeed, phi k satisfy the condition modulus phi k of x minus y naught less than or equal to capital M into x minus x naught for all x in I. And the definition for Lipschitz condition, that f be a function defined for x comma y in a set S, we say f satisfies a Lipschitz condition on S if there exists a constant k greater than 0 such that modulus of f of x comma 1 minus f of x comma y2 less than or equal to capital K into modulus y1 minus y2 for all x comma y1, x comma y2 in S. The constant k is called a Lipschitz constant. So the theorem we are going to see is the convergence of the successive approximations. So this is the statement of the theorem, that f be a continuous real valued function defined on the rectangle R such that modulus of x minus x naught less than or equal to a, modulus of y minus y naught less than or equal to b, where a comma b is strictly greater than 0, and let modulus of f of x comma y less than or equal to capital M for all x comma y in R. Further, suppose that f satisfies a Lipschitz condition with constant k in R, then the successive approximations defined by this will converge on the interval I such that modulus of x minus x naught less than or equal to alpha, which is the minimum of a comma b by m, to a solution phi of the initial value problem y dash equal to f of x comma y comma f of phi of x naught equal to y naught. So by the previous theorem, the successive approximation phi k exists and continuous only. Also we have x comma phi k of x is in R for all x in I, and phi k of x minus y naught, the absolute value, will be less than or equal to m into modulus x minus x naught. So this theorem will be constituted of 4 parts. So in the first part we will see the convergence of phi k of x, and in the second part we will see the properties of the limit phi, and in the third part we will estimate the absolute value of phi k of x and phi k of x, and in the last part we will show that the limit phi is a solution. So now we will enter into the proof of this theorem. So we are writing phi k of x as like this. This phi k of x is the sequence of partial sum of this series given by equation number 2. So to prove this sequence converges, it is enough to prove that the series converges. So first we are going to prove that the modulus of phi p of x minus phi p minus 1 of x less than or equal to m into k power p minus 1 into modulus x minus x naught whole power p by p factorial. We are going to prove this by induction on p. When p equal to 1, we are getting this value. So this equation is true for p equal to 1. For also p equal to 2, substituting the value of phi 2 and phi 1, we will end in like this. So y0 and y0 will get cancelled, and the modulus of this will be less than or equal to integral modulus, and this value satisfies the Lipschitz condition with constant k in R. So we are getting modulus phi 2 of x minus phi 1 of x less than or equal to k into, so this value m into integral 0 to x p minus x naught dt. So by integrating this value we will get like this. So we are ending like this. So this result is true for p equal to 2. So we are going to assume the result is true for p equal to m, and we are going to prove for p equal to m plus 1. So considering modulus phi m plus 1 of x minus phi m of x, so putting this value and y naught will get cancelled. modulus integral will be less than or equal to integral modulus, and since f satisfies the Lipschitz conditions, so this will become like this, and k will come out, and this modulus value we have assumed already, so substituting this value, and again we will integrate. So after integrating, we have to apply the limit, and then we will get this result. So we have proved this result is true for p equal to plus 1. Hence, modulus of ip of x minus phi p minus 1 of x less than or equal to m into k power p minus 1 modulus of x minus x naught the whole power p by p factorial, where this k is the constant and m is the bounded value of the function f. So similarly, this result is true for x less than or equal to x naught also. So now we are considering the p term in the series. So this term will be less than or equal to m by k times the p term of the series exponential of k times modulus x minus x naught. Since the series e power k into modulus x minus x naught converges, by comparison test, this series also converges. Hence, the series taken in the equation number 2 also converges. Therefore, in sequence of partial sum also converges. Therefore, we are taking the converging limit of the sequence phi k of x as phi of x. So now we are going to see the properties of the limit phi. So first we are going to prove that the phi is continuous. So for that we are considering modulus of phi k plus 1 of x1 minus phi k plus 1 of x2, and then applying the limit, and the modulus of integral will be less than or equal to integral modulus, and this function is bounded by capital M, and applying the limit I will get like this. So if x1 tends to x0, then this value tends to this, therefore my function phi is continuous. So also we are going to prove that the x comma phi of x is the rectangle. So for getting this, we are going to substitute x1 equal to x and x2 equal to x0 in this equation. Therefore, we will get modulus of phi of x minus phi of x0 will be less than or equal to p. So which implies this x comma phi of x in the region R. Since region R, modulus of y minus y0 less than or equal to p. So in the third part, we are going to estimate the value of modulus phi of x minus phi k of x. So substituting the value of phi of x and phi k of x, and the difference between these two will be p equal to k plus 1 infinity series. So modulus summation will be less than summation modulus. We have already found out this value. Substituting this value, we will get like this, and we are taking k plus 1 infinity summation k power p modulus x minus x by p factorial. So putting this value as alpha, so we will end like this. So in this term we are taking p power k plus 1 and alpha power k plus 1 as common, and we will end like this. This will value be less than or equal to these terms. So this is nothing but e power k alpha. So we have found out the value of this. So now we are going to prove that this phi is the solution of the initial value problem. To prove that phi is a solution of the initial value problem, it is enough to prove that phi is a solution of the integral equation. So to prove that, we are taking the successive approximation formula phi k plus 1 of x. So by applying the limit on both sides, this will end up with phi of x. So it is enough to prove that this limit is nothing but equal to x naught to x f of t comma phi. To prove that, we are going to consider the modulus of these two difference. So again, modulus integral will be less than or equal to integral modulus, and this value will be less than or equal to k times the CCF satisfies the Lipschitz conditions. So we will end like this. So this value we have already found out in the C. So applying that limit. So we are taking the remaining terms as epsilon k. So where this epsilon k is nothing but the k plus 1 determining e power k alpha, which is convergent. So epsilon k tends to 0 as k tends to infinity. Therefore this side tends to 0 as k tends to infinity. Therefore this is equal to this. Therefore my solution phi of x equal to y naught plus epsilon k x f p comma p. So we have proved that this phi is the solution of the integral equation, so which implies this phi is the solution of the initial value problem. So to prove this theorem, it is enough to prove the third part in the previous theorem. Thank you.